nanohub.org.
Online simulation and more for nanotechnology.
This is the last topic. It's going to be on optimization of very expensive functions. These functions could either be simulators or it could be experiments. What we're going to do today is about deterministic functions, functions that have no noise, but this easily generalizes to noisy functions. For example, experiments with noise or simulations that are stochastic, like Monte Carlo simulations. And I'll show you some reference at the end about the generalization. Alright, so the objectives are to quantify the value of information extracted from an experiment or a simulation. So the idea for solving optimization problems that involve an expensive objective function, an expensive simulator, is to sequentially design where you evaluate your function to extract the maximum amount of information with a minimum amount of cost. Okay? And we're going to use this idea, the value of information, to optimize expensive black box functions. So the problem is like this. We're going to have a function f of x. That f of x, so x is whatever you want to optimize over. Okay? It's your design parameters, if you like. I don't know, if you are optimizing a bevel gear, it would be the number of teeth, the radii, the material, whatever describes that object or thing or whatever you want to call it. Okay, so our design parameters are x, and f of x is basically an objective function that you would like to maximize. So, you know, whatever you are interested in maximizing, right? And that f of x could be, doesn't have to be an analytic function. Actually, if it is an analytic function, you don't even need what I'm talking about, okay? So f of x could be, for example, a finite element model that requires you to run a script that sets up an ANSYS input file, then runs ANSYS on a cluster computer, grabs the result, processes the result, turns them into a single number that you're interested in maximizing, and gives it back to you. That's what f of x could be. Or f of x could be the result of an experiment. It could be, for example, you give x, and f of x is basically a PhD student taking x, saying, okay, that's x. Let me set up my experiment so that x. Okay, so he sets up the experiment, runs it, goes for a coffee, comes back after 2 hours, realizes that something is wrong, does it again, right? And then when he gets the results, he takes the specimen out, puts it in another machine, measures something else. Then he puts that on MATLAB, grabs f of x from some analysis, and gives it back to whatever this thing is doing. Okay? Or it could be, you could have a website, for example. We'll see an example like that later on. And x could be the design of the website, where things are, or what kind of prices you use for different things that you may want to sell. And f of x could be the number of clicks that you measure over the period of 1 week, or the sales you do over a period of 1 week. Okay, so it could be that. In any case, the problem is always maximize f of x. All right? And we're particularly interested in the following cases when the objective is very expensive to evaluate. And by expensive here, I either mean expensive in dollar amounts. So its evaluation of f of x may cost, I don't know, $100, $2,000. But this is, of course, subjective, okay? Or in terms of time. But time is money, so it's the same thing. And the other thing that is important is that you don't have gradients. Okay, so we're not going to assume that we have the gradient of f with respect to x. Okay? And of course, be reasonable, the techniques that I'm going to talk about do not work for very high dimensional x's. Right? So if you have anything that has more than 30 parameters, and 30 may even be a lot, you need to approach the problem in a different way. But if you have 4 or 5 or 10 x's that you may want to tweak, these techniques would work. And there are a lot of problems that fall inside this category. Alright, here's an example of the oil well placement problem. So X is the well locations, where are you going to drill, which of the wells are going to be injection wells, which ones are going to be production wells. And then you can simulate and see how much oil you're going to extract as a function of time. And then you can try to maximize the net present value of the investment. Okay. And then for every selection of the X, you have to run a simulation. Okay, not even one simulation. Let's say one simulation of this oil reservoir for, I don't know, 20 years may take like 1 or 2 days because you're uncertain about the permeability field. You may want to use a sampling average over the permeability field and do like 1,000 simulations. So one simulation that averages may take like a month. Okay, of course you can accelerate that, but you're not gonna bring it down to a minute. Okay, it's still going to be expensive. Another example, you may want, this could be an example from pharmaceuticals, for example. You may want to say optimize the structure of a molecule, or in this particular example, we try to find the structure that minimizes the energy, so the stable structure. Right, so if you minimize the free energy, you can find the stable structure under different conditions. So here, X is basically the geometry of the molecule. It's basically the Cartesian position of each one of the atoms that make up the molecule. F of X is the energy which you can if you calculate with ab initio methods, doing basically solving the Schrödinger equation or an approximation like density functional theory. It may take I don't know, a few minutes. For the molecule, it's not really that difficult to do it. But it's not immediate. It will take a while to give you the energy, and you want to do it in the minimum amount of time. An example from website optimization. This is an actual example. This is what they actually do. So X could be the web design or other attributes of your website, and what you measure could be the number of views, or the seconds per view, or the amount of sales. I had that minus there probably because in the first version of the slides I used minimize f of x instead of maximize f of x, so forget about that minus up there. And for example, Yelp uses that. Okay, Yelp uses this kind of tell you the truth, Yelp doesn't really look that good to me, but but anyway, that's what it uses on the background, and a lot of sites use this technique. And you can also use it to, so if you're doing robotics, typically the mechanisms you have to analyze are so complicated that you cannot really do the dynamics. And especially when you want to design controllers for them, the dynamic programming problem that you may have to solve is very complicated. So it is much easier to just try different controllers until you find the one that works. Okay, so what you can do is you can say X is basically a description of my controller for a robot, and then f of x is some quantity of interest that quantifies, let's say, the stability or something that you may be interested in, and you may actually automate the process of looking for the best controller, and you get things like this. For example, I mean, I'm sure these examples are at least two years old. So this is an example of a bipedal robots trying to figure out the best controllers by solving an optimization problem on its own. So it's basically trying the controllers that maximize the value of information one by one until it learns how to walk. Okay, so it's trying, obviously this one cannot be completely automated. Somebody has to pick it up and, you know, let it try the next controller, but eventually it learns how to walk. And here's another example from ETH.
which safely optimizes controller parameters during operation. The goal is to maximize the controller's performance for a step input, such that the vehicle quickly comes to rest at a newly assigned location. Our initial controller performs poorly, but stabilizes the quadrotor. The algorithm then intelligently selects and evaluates new controller parameters for which sufficient knowledge about their safety is available. As we evaluate different safe controller parameters, we gain more knowledge about the underlying performance function, which is approximated by a Gaussian process. Since safety is guaranteed, the entire optimization routine can be carried out automatically and without any crashes. The algorithm terminates once we have gained sufficient knowledge about the best controller parameters. Here you see them highlighted.
So another thing that I want to point out before this guy brags about what they did, this is basically their design space is two-dimensional, two parameters describe their controller, and this is the objective function which is not known to them, but they can measure it, right? So they say, here's the controllers, try to go from, this is the control parameters, try to go from point A to point B, let's measure how much it takes, how much it takes is basically minus that is what we want to maximize, right? So this is what you see there, this kind of measurement, right? So they don't even know that function. They just measure it with a drone. And then the algorithms that we're going to talk about, these Bayesian global optimization algorithms as they are known, they adaptively learn this surface based on observations of X and the quantity of interest, right? So they use the observations to learn the objective function, and then they sequentially suggest new points to try out, okay? And the characteristic of these algorithms is that they ignore, they're going to explode a little bit the space of controls, but they're going to ignore regions in space about which they're quite certain that they are suboptimal. So you see here that the inputs they try get concentrated towards the maximum.
The resulting learned controller significantly outperforms the initial one.
Anyway, at this particular example, again, it's a drone. It's not that complicated to model the dynamics. So you could probably do it with physics, right? But for more complicated things, this is sometimes the only thing you can do. Yes?
How do you know the region of space is not optimal when you haven't tried out a point in that space?
You extrapolate, right? So if you try at X and you measure Y, because you expect this objective function to be continuous, you can say what's going to happen in between, right? That's how you know. You don't really know. You're going to have to go and visit it, right? But because you are using the X and Y's you have measured to build the Gaussian process, to do Gaussian process regression, you're able to say for any given point that you haven't tried, what do you think the performance is going to be with error bars, right? So if you know that if your Gaussian process predicts that the performance is going to be very low, even if the error bar is big, if it is not sufficiently big so that there is a possibility to get you above the currently observed maximum, it's going to ignore it. We will see the details in a while. Questions? Okay, so it is extremely useful to be familiar with these techniques. Bayesian global optimization can solve a lot of practical problems when it comes to people who optimize simulations or people who try to optimize experiments. And yes, that's it. All right. So other examples, model calibration, right? So if you want to do model calibration the traditional way, where you minimize a loss function or you maximize the posterior, nothing is stopping you from using Bayesian global optimization to solve this optimization problem, right? So if you don't want to create a surrogate of your model and you want to use one of the optimization-based approaches for model calibration, then you can just do it, etc. Okay. And there are actually probably more than one, but there is one company that I know. It's not a startup anymore. It's I mean, okay, it's 3 years old. There's this company, SIGOPT, which was started by a friend of mine from the Applied Math Center at Cornell, Clark Scott. So this guy started this company that sells Bayesian global optimization services, right? So he has an API that allows you to, you basically give him X's and Y's, and he tells you what is the next X you should evaluate your objective function on. And that objective function could be an experiment, or it could be a simulator. And they do lots of fancy stuff. They try to completely automate this process, but just to give you an idea, right? So I think they have at least 500,000 or 1 million of funding secured up to this point. They were charging $1,000 a month for this service. And you guys can now do it. Okay, so you can go ahead and charge $800 a month and do the same thing. Okay. And there, of course, libraries that it is actually very easy to implement this from scratch, as you will see, because it is not that difficult. As soon as you have a Gaussian process library, because Gaussian processes are on the background, it's quite easy to do it. And there's some free options. PyBGO is what we've done here at Purdue with Pius, and GPy, but we don't maintain it that well. Okay, it still works, but we're not really adding stuff there. And GPy OPT is basically from the guys that wrote GPy. It's an extension of GPy that does optimization. That's pretty much it. Okay. All right. So if you want to try out stuff, you do pip install GPy OPT. Here's the idea. Okay. Now let's start talking about this. We have some observed data, X and Y's, okay? So you don't start from nothing. You do a bunch of experiments. I was going to give you an idea of what your Y's are. And then you fit a statistical regression model that's going to get you from X to Y. Basically, you do Gaussian process regression, right? And then for new candidate designs, for an X that you haven't seen, you quantify the value of information. You quantify how much you're going to gain if you in expectation, if you did a simulation or an experiment at that X. So this is a concept from economics, the value of information, about which we're going to talk in a while and going to understand, where it comes from. But it's really just that. How much am I going to gain if I do an experiment at X? How do I expect to gain? All right, and then as soon as you can quantify how much you can expect to gain for any given design that you may try, you pick the one that has the maximum value of information. Okay, and you do that. So first you quantify the expected value of information for everything that you may do, then you pick the one with the maximum value of information and you do that experiment or simulation. Okay? And you add it back to your data set, and you go back and you repeat. That's the idea. Okay? That's what happens. So you start with some X's and Y's, you build a Gaussian process surrogate, you use the Gaussian process surrogate and your mind to quantify the value of information, the value that any design you may try out may give you. Then you find the design with the maximum value of information, you do that, you add it back to your data set, and you repeat. Okay, and you repeat until you run out of money, okay? Or if the value of information is low. All right, so here's how it's done. You have some data, X and Y. You build a surrogate. That's the mean and uncertainties. You need the uncertainties for this kind of thing to work. The uncertainties are used later on. And one of the surrogates that we may use, of course, is the Gaussian process regression. Right? So remind you that the Gaussian process, you start with some observations of x and f, and then you can you assume that these are all the joint distribution of the function values are multivariate Gaussian with a covariance function as given by a covariance matrix as given by the covariance function, etc., etc. Go back and read about it, and then you can use the Gaussian process to predict your objective function at any test points you want. Right, so you can say, okay, let me just take lots of x's, lots of designs, and just predict what the function values are going to be there, and this is what you're going to get, right? So this is your prior Gaussian process. You see data, and then the data just grab the functions and make sure that they pass through them, and then you have a little bit of residual uncertainty, right? And what you really want from the Gaussian process is the point predicted distribution, which basically tells you what y is going to be, what the objective is going to be at a new x, given the data you have seen so far. So you see here, now what exactly is that? Go back again over this lecture, but here's how you read it. What do I think y is at x after I see these observations? And what you think is, well, it's going to be distributed according to a Gaussian with this mean that comes from, it's the posterior of the Gaussian process, and a posterior predictive variance that comes from that guy. Okay? And it is like that, so that's the mean. It's a solid blue line, and the variance gives you -2 times the standard deviation, the square root of the variance, and +2 times the standard deviation. Predictive standard deviation gives you these nice error bars. Okay, and we're actually going to use that. Alright, so remember that what we want to do is we want to maximize, right? We want to maximize f of x. Here, f of x, f is known at these 3 points. It is not known anywhere else. Okay? Everything else you see here is just a guess about what f of x could be. Alright, so let me just zoom in here so that you can see it. So these are actual observations. Now the blue line is a Gaussian process mean prediction for f of x, and the shaded area is the uncertainty of that Gaussian process regression. Okay, so this is, you don't really know what f of x is here. Obviously, you kind of know what it is here, you don't know what it is there. Okay, but that's all the information you have. Now, I'm going to show you how an information acquisition function good information acquisition function would look like before I introduce them, just to give you an idea. So this green line here is the expected value of information, if you like, that I would gain if I did a simulation at one of these points. Okay, so if you simulate here, you don't get anything. It's not valuable to simulate. So look, what if I simulate exactly where I was before? Well, that's garbage. Don't do that. That's zero information. You already know what it is there, right? So what if I simulate here? Well, that's also zero. You are completely sure about what the value of the function is there. Why would you do it again, right? But what about this region right here? Maybe, it will pay off to simulate there. Well, look, you have two simulations that are close together, so you kind of know that f of x would go like that. I mean, it could do things in between, but it would be like that. I mean, there's not a lot of value in doing this simulation, right? And that's exactly what it tells you here. But it does tell you that there is a lot of value of doing simulations here, right? Why does it do that? Because there's a lot of uncertainty. So it says, I don't really know. Right, so I see that, the trend is like that, but this is not, I'm not sure about that. You see these huge error bars? It could really go up there. So there's a lot of value in doing this simulation. And actually the most informative point to simulate will be this point right there at the very edge, right? Because there is a lot of uncertainty for that point, and at the same time, it kind of feels that there is a trend like this. So it's very likely that the function will go up there, the actual function. Yes?
What is the leftmost cross? The green line below it is not zero.
Well, it goes up to, I'm excluding this point at the very edge for some reason.
That black cross.
Why is it not zero? This is probably a numerical mistake, most probably.
Why is the green line zero?
Why is the green line zero here? Why is it not zero there?
At point zero.
Here?
Yeah.
It should not be zero. It should be as high as possible. I don't know why it is drawn like that, but this is not correct.
Just maybe put it there to mention that's the maximum.
Oh, yes, exactly. Yes, I remember. This is just a vertical line I put there to indicate where the maximum is. Now I remember, I did it 2 years ago. You will see it in the next slides. So it's just a vertical line that I put there to show you where the maximum is. Okay? Okay, so if the maximum was there, I would put that line there. So you will see it changes later on. Thank you. See, it's hard to remember what you did 3 years ago. Yes?
So it seems more uncertain at the right-hand side than the 0 point.
Yes, it is. There is, you look at how far away these 2 points are.
Yeah, but why does the 0 point have the maximum?
So that's a very good question. So we haven't really defined the information acquisition function, right? So we will define it in a while. But, and there are many choices for the information acquisition function, as you will see later on. But the characteristic of a good information acquisition function is that it will balance between exploring the space, meaning it will balance between visiting regions that it hasn't visited before, like this one, okay, and exploiting what it has already found, right? So right now, it kind of sees a trend here. So it says, maybe it goes up. Maybe I should exploit this knowledge and try to evaluate things here. Because it's kind of like a gamble, right? So it's very probable that it's going to go up. So I will go and do this. But at the same time, you know, you have to explore. There's a completely unexplored region there you should visit. So a good information acquisition function would balance between these two. Exploring the space you haven't visited and exploiting what you have already found. And you will see this later. Yes?
So the objective in this problem is to find the maximum value of f of x or find the data points of.
Find the maximum value of f of x.
So that's why the information is like, even if there is a small gap in the space, we have to go there because we feel that.
Yes, it tries to exploit what it knows. So it says, look, there is quite a bit of uncertainty here, smaller than what I have here, but here it is more likely that I go up. That's how it thinks. Anyway, yes?
There can be maximum point between the two black dots also.
There could be, but it is very unlikely. That's why the value of information is very small. Make sense?
I mean, uncertainty can be high between also, like we don't know.
No, we do know here because we have fitted the Gaussian process regression. So that's the representation of our uncertainty. We're more uncertain here than we are there. Okay? So here we are less uncertain, so we don't really want to explode this region. And at the same time, it's very unlikely that the maximum is between these two. There's not a lot of room for the function to go up. Anyway, you will see now what's going to happen. Okay, now let's do the math. But anyway, the idea would be, as soon as you have the information acquisition function, you find its maximum, you go ahead and you do that simulation, you add it to your data set, and you repeat. Okay? So if you do add this function evaluation, then the new information acquisition function will look like that. It will tell you, look, now I want to explore this region. I have no clue what's going on there. So it tells you you should go and do a simulation there. So that's the point that maximizes the value of information. So if you go ahead and you do that, and you add that observation, that's the observation that we just added, and you update your Gaussian process, then you get this new blue line, right? And the new information acquisition function looks like that. Look at what happened. Exactly at this point, the value of information goes to 0, but because there is still a huge gap between these two, right? It still wants to explore that region, and there is also a huge gap between these two, and it wants to explore that region as well. And that's what but it wants to go closer to this point because it is more likely that the maximum is closer to that point than to that point. And if you do add that, then the situation becomes like this, and then it has basically located the maximum. Yes?
So, in these processes, with the Gaussian process you're actually using to begin with, has there been a step that's already been chosen to kind of pick what the right parameters of the Gaussian process are?
No, you optimize them every time. Every time you add one point, you optimize them.
The first Gaussian process that you use, I think is that evidence.
You have to start with a few x's and y's, right? So if you start from nothing, then you basically pick a random point. Okay, and then whatever you do with the Gaussian process, unless it's not gonna tell you anything, it's just gonna tell you don't simulate on that point. Okay, it will force you to simulate at the boundaries. That's gonna happen. So when you start these algorithms, the best thing to do would be to start from a Latin hypercube design. So you say you have a budget of 100 simulations or 100 experiments. Well, the first 5, pick them randomly. Then start this thing, okay? Because it is actually possible to get garbage if you start from very few simulations and you're very confident about the hyperparameters of your Gaussian process and all that. Anyway, so you see, you at that point, you go to iteration 5, it has basically found a maximum. So now if you keep, and if you look at the scale here of the value of information, it goes down if you look at the scale. And it will keep picking points there, okay? But the value of information will be very, very small. Yes?
What justifies the use of Gaussian process here?
That is the easiest the easiest regression method with quantified uncertainties for the prediction.
Why? So why?
The one that works best out of the box without you knowing what's going on with it. But you could use anything else. You can use everything I'm going to talk about can be done with any Bayesian regression method. Any regression method that gives you predictive error bars for f of x. So anything that gives you f of x with a mean and a variance can be used. Doesn't have to be a Gaussian process. But Gaussian process is the best regression method when you have continuous functions that are smooth and relatively low dimensional x's.
Is it experimental or theoretical?
No, it's empirical. I'm telling you this. Why would you use Bayesian global optimization with Gaussian processes and not with what else? I don't know. Everything else is more complicated than Gaussian processes. And it will take more tweaking to make it work. But you could do it. Now, if there are 3 packages out there that use Gaussian processes on the background to do Bayesian global optimization, then there's probably empirical evidence that it's best to use this as your backbone. And there is also a theoretical result that guarantees that for a special information acquisition function, this procedure will converge to the maximum. There is theoretical evidence to the global maximum. Anyway, so here's our problem again, right? So that's our problem. All right, so now I'll tell you about the information acquisition function, okay? Now, if you really think about the problem is not where to pick the next simulation. The problem is what policy to follow for picking simulations. That's the problem, right? Because your state of knowledge, every time you pick a simulation, is going to change. So you want to optimize over the ways you can pick simulations, not just optimize the next simulation. Okay, that's the ideal problem. So you want to also optimize over when to stop. This is a dynamic programming problem. It's called the optimal stopping problem. It is, if you try to think in that way, you'll probably get a problem that is more difficult than the one you have to solve in terms of complexity. Okay, because these are very complex problems to solve. If your objective function is ridiculously costly, like if people die, for example, every time you evaluate it, then you will like to consider thinking about formulating it in a dynamic programming framework. Otherwise, don't worry about it. Because it's too hard to mathematically pose the correct problem. To solve it, to pose it, it's not a big deal. To solve it is the big deal. We use ad hoc approximations to it. Okay? And the ad hoc approximation we're going to use is that instead of looking at all the future, we're just going to look at the next step. So we're going to employ what is known as myopic information acquisition policies. So we're going to restrict our attention to information acquisition policies that only look one step ahead, as opposed to information acquisition policies that consider 5 steps ahead or all steps ahead, which are much more difficult to formulate and solve. But again, the costlier your objective function is, the more you should be motivated to go beyond one step look ahead information acquisition policies, and it will pay off. What would you have to consider? You will have to consider also the amount of effort it would take to pose and solve the information acquisition problem, right? Because it will be that difficult that you will have to make it part of the problem. Anyway, now let's concentrate on myopic information acquisition policies, which is what I showed you before. This is the kind of algorithm we see, selecting one by one by maximizing the value of information. And the value of information depends on what you want to do. Okay, so here we just want to maximize a function, so it depends basically on that objective function and what we think about that objective function. And to quantify it, we must be able to assign probabilities over all possibilities, and that's what the role of the Gaussian process was, to tell us what f of x we should expect at a new x. And we must be able, so that we do it with Gaussian processes, and we must be able to quantify our profits or losses if at a given x we observe an f of x. So we must be able to say, look, if I go to x and I observe f of x, how much would I gain? How much would I lose? Maybe the answer is just f of x, okay? I'm just saying. But maybe it's different. All right. So the value of information is a concept from economics. It's very, very easy to understand. So the value of information of x, you think of it as the value of doing a hypothetical simulation at x. It's going to be how much you expect to gain if you do a measurement at x. Okay? That's the definition of the value of information. So it's going to be how much you expect to get as an income if you do a simulation at x, minus the current best alternative. So right now, you already have some value because of whatever you're doing, right? So if you go and simulate at x, you're going to get perhaps a better f of x. What is going to be the increase in value, right? What is going to be the increase in value? This increase in value is the value of information. So look at what kind of the words I'm using. The expected gain, right? So if you stop your simulation right now, if you stop your optimization right now, you can just pick the best f of x you have found. That's your value. But if you decide to continue, you must talk about how much you can gain, you can expect to gain on top of what you already have. And to get that, you must think about how much you can gain from x minus what is your current best. Okay? And how much you can gain from x is basically what you expect to get from x as a form of income, like f of x, minus the cost of doing the simulation. Okay? So this is it basically. And of course, because we are engineers, we can say, well, cost is 0. Okay? And the expected income, if I measure x, is f of x. And the current best alternative is the maximum f of x I have observed so far. And be done with it. Okay? And that's what we're going to do. But, again, it may pay off in another situation to actually think about this in terms of value of information. Alright, so acquisition functions. So most of the times we don't have the details to find the value of information, or we just don't want to do it, okay? And we just approximate the value of information in different ways. One way to approximate the value of information, which is actually very bad, but I'm just going to say it to you because it is commonly used, is the probability of improvement. So you say that x, the value of x is basically as much as the probability that a simulation at x will improve the best that I have right now. The expected improvement, which is quite good, and this is what I suggest that you should use. The knowledge gradient, which is the best, but it's not very easy to implement. It's actually not implemented in any of the packages that are out there. Okay. An expected information gain. So the knowledge gradient is what you should use. It's actually the value of information, period, if everything is in economic terms. And that's what you should use. The expected information gain comes from information theory. It's basically the Kullback-Leibler divergence of the probability density describing a state of knowledge about the location of the maximum. And this is what you should use if there's really no economics in your problem, but it is also very complicated to implement. So, ridiculous, correct for the correct value of information, but a little bit complicated, can be considered as an approximation of that, and works quite well. And there are actually theorems that prove that this converges. The best if you don't have an economic framework, but a pain in the butt too. Implement. And there are more, but I think that everything else is basically garbage. Okay? So let's look at some of the garbage first. Okay? So what is the natural... I mean, if you just pick a random engineer that hasn't seen expected improvement before, and you ask them, okay, you're maximizing a function, you have seen these x's and these y's, you have built the surrogate, here's the surrogate, find me the next x that it makes sense to simulate. It's very likely that they're going to answer, well, you should pick the one that has the maximum mean. Right? So use as an information acquisition function the mean. So I will mean pick this point up there, okay? The one that maximizes the blue curve. Don't use that. This is garbage. This will not give you the global maximum. It will stop very fast. It is a self-fulfilling prophecy, if you like. It will converge somewhere that it's not going to be the maximum. Okay? It only exploits what you know. We need to add a few elements of exploration to it. Now, a very good and simple modification to that is to use the maximum upper interval. So you say, I'm going to use as an information acquisition function m of x plus psi times the standard deviation. So you're basically following the one contour, let's say iso probability contour in the iso predicted probability contour. So you're following basically, let me just draw it here. You're following a line like that, right? So mu plus psi times sigma, right? And this is now This is now your information acquisition function. So you just select the simulations that maximize this line. And that psi is basically a way you can use to balance exploration and exploitation. And you can show that for, if I'm not mistaken, for any psi, you just have to make it a little bit bigger than 0. This algorithm will find the global maximum. It will converge. So if you continuously add the simulation and maximize this information acquisition function, and then you do Gaussian process regression and you repeat, it will go to the global maximum. It's called the maximum upper interval. All right, and of course, by controlling this psi, but of course, it converges to the global maximum in the limit of infinite simulations, right? So as we have said, this is what happens with mathematical theorems. They're all in the limit. If you stop before the limit, you don't know where you are. Okay, and you can use that psi to either exploit more. If you make it smaller, you're going to exploit more because you will use more information from the mean. If you make it bigger, you're going to explore more. You're going to give more weight to the predictive uncertainty. Okay, probability of, yes?
What's the difference between exploit in this problem? What do you mean by exploit or explore?
Okay, by explore, I mean visit regions of the design space that have high uncertainty. Okay? High uncertainty. By exploit, I mean visit regions of the design space that are likely to give you a high value of f of x. By exploit, I mean use the information you have to select a design that is very likely to give you a high value of f of x. So you either explore, just go and look at places that you haven't visited before, or you exploit what you have already seen. So right here, for example, you say, I've seen a big X here, so let me just exploit this fact and look around here and ignore this. Right? And you need to balance between these two. Anyway, probability of improvement. Let's keep it. Don't use it. Okay? Seriously, don't use it because it also doesn't converge. It makes sense, there's an analytical formula, but it doesn't work. Expected improvement. That's what you should use. And here's how it goes. Let's go over the derivation because it pays off to think about it. Because you may have to modify it in your problem. If, for example, you have noise, you may have to modify it. All right, you start by writing down the current best. What is the best f of x you have seen so far? So this is just the maximum of the y's you have observed. Okay? So you say, here it's going to be this guy over there. That's the best. Okay? I have seen. Now, you say, let me do a hypothetical simulation at x, and let's assume that I observe y. Okay? So go to x and assume that you see y. The improvement you're going to get in your objective by this hypothetical simulation is this. So it is 0 if y is smaller than the current best you have found. Otherwise, it is the difference between the current best and y. Right? So let me repeat. You say, that's my current best, this thing, all right? So you say, if I go to x and I observe y, how much will I improve? So if the y you observe is smaller than the current best, you don't improve, 0. If the y you observe is greater than the current best, then you improve by this much. Okay? So the improvement you get if at x you observe y is the maximum of 0 and y minus the current best. Okay? But you don't know what y is. Okay? It's a hypothetical y. So you use now your current state of knowledge, which is encoded in the Gaussian process, to integrate over this hypothetical y. So you say, this is my improvement, but I don't know what this y is. Let me integrate out using my Gaussian process. Now this is a normal distribution, multivariate normal, right? So it's the multivariate normal of the Gaussian process. This guy, basically. Okay, that's what it is. So it turns out that this integral can be done analytically. And it is this. Okay? So you have here the mean of the Gaussian process minus the current best, the cumulative distribution function of a standard normal evaluated at this thing. Then you have the predictive variance, the predictive standard deviation, the PDF of a standard normal evaluated at that. Why is it like that? Well, it's just like that, okay? There's no answer why. Because this integral is this. Now, do you like this as a measure of the value of information? Do you like it as a value of information, as a measure of the value of information? Then that's what you should use, okay? If you don't like it, that's also fine. Pick something else. Do the integration from scratch, okay? All right, and you see here the balance between exploiting. Whatever has m of x in there, it is exploiting. Whatever has sigma here, it's the exploration part. So this is exploitation part, this is the exploration part. You see, it does put some weight on high variances, it does put some weight on high means, and it uses these quantities to balance things. Why? Because that's what this integral gives. All right, so let's look at, yes?
What are the fives?
I just told you, right? So it is the CDF, the cumulative distribution function of the standard normal, and the probability density function of the standard normal. Because this is a capital phi, which is the CDF, the cumulative distribution function, and this is the PDF. This is the derivative of this. This is the CDF, this is the PDF of N01 of N01. They're different. Because this integral, if you do it, you will find that. Go ahead and do it. You take this, the PDF of that, you plug it in there, you do your calculus stuff. It's less than 3 lines. And you will get this. If you rearrange terms and you transform the integrals. Make sense? All right. And that's why I suggest that expected improvement is the best thing to use, because it automatically trades between exploration and exploitation. And let's see how it works. So I think I've showed you this before. So this is the expected, so here I already added that point. So you see here the expected improvement as a function of x. It is telling me go ahead and do this simulation. So it's exploring now, right? It says let me explore. It found that point over there. Then we are going to use this point to update the Gaussian process. Here we have updated the Gaussian process. This is the new expected improvement. You see, it automatically becomes 0 wherever you have observations. Why does it become 0 there? Because if you look at the formula, it is exactly 0 there. That's why. And then it kind of exploits, right? It kind of exploits. It says, let me look around this because I think that this is where the maximum is. So it exploits, and it's quite right actually. So you see how its state of knowledge changed for this side, observing a third observation right there, so that these 3 are in a row, made it very likely that this goes down like that. So now it is absolutely sure that this is where it is, so it just exploits. Okay, and if you add it, then it wants to exploit even more, and it will just give you stuff there. But let's see what happens. So let's see what happens if we plot the value of information as a function of the iteration number. All right, so we would expect, as we keep adding simulations, the value of the marginal value of information, how much we gain every time we add the simulation, to gradually go down. But what has happened most of the times is that it goes down, and then at some point we learn something surprising that changes our state of knowledge. Okay? And for that step, the value of information may go up again. And then it will go down eventually. So you get things like that. So something happened here. What happened there is that we made an observation that changed our Gaussian process dramatically. Right, so this point right there is where we got this unexpected information, and this phenomenon, the phenomenon that the value information, the marginal value information, the information gain, if you like, how much you gain every time you have the simulation, does not go monotonically down. It's called the S-curve phenomenon of information. So if you look at the information gain, it will go down, and then you discover something, it will go up, and then it will go down again. So it always does stuff like that. And there's no reason why you should have one S. You may have more S's, right? So this may happen again here if you see something unexpected. Okay. So this happened here, right? This is where the unexpected information came. So this was our state of knowledge. And the expected improvement told us to evaluate this point and look at what we expected. We expected this point to be between this and that point with 95% probability, and it was actually up there. So this changed completely our state of knowledge. Yes?
I don't understand why it's up there.
Oh, it is just up there.
I mean, if I had a different approach, it might have been somewhere else. No.
No, this X, this cross, is real. It is there. No matter, the blue thing is what I think about where the crosses are. The crosses are wherever they are.
Is it there because we actually knew the problem beforehand?
There is a function f of x that we evaluate to get the crosses. Okay, but I don't show it there. That function goes like that. Okay, but I don't show it there because you don't see it while you're doing this thing. You only see it after you evaluate it. So when you have seen these points and you argue about that function, you think it is very unlikely that it has a value there. But this doesn't mean that it cannot have a value there. It can have a value anywhere it wants. So when you go and you do the experiment, it actually turns out to be there, which means that you have to change what you thought about it.
On the previous page. So why is the value negative?
Because it's in the log scale. But good point.
Why does it go up?
Right there?
Yes.
That's what I've been talking about, right? So right there, at that particular point, this is my state of knowledge.
Yeah.
Okay? So I get an unexpected piece of information that changes my state of knowledge completely. So from this state of knowledge, I go to this state of knowledge.
Yeah.
Okay? So look at the value of information here. It was very low, 0.02. And then after, because, I was quite sure that the maximum is not there. That's why it was so low. But when I added it, it changed my state of knowledge completely. And now look at the value of information. It went up to 0.14. So that's what happens. What does that tell you? This tells you that you cannot use the value you gain to stop the algorithm. You cannot say, when the value I gain becomes smaller than a threshold, stop. because you may see something unexpected and then you're going to go back up again. Okay? Yes?
So in this case, we have to have a f of x that is relatively smooth without great transients in between, right?
You define you have to.
I mean, if we have like great transients in between where our function is like very large, but that value has to be neglected. So we have to design our f of x depending on that.
No, your f of x is whatever it is. You don't even know what your f of x is. Your f of x is a black box function. If you knew what f of x is, in the sense that if you knew what is inside it in detail and you could argue about it, then you should not use these methods. You should exploit what you know about f of x. Now I'm talking about an f of x that you don't really know what it is. Okay? Now if it happens that it is smooth, this algorithm will converge. If it is not smooth and you do not know it, you will still get something better than doing nothing.
I'm saying that we do not know exactly what is f of x is, but we know that initially there is a transient phase and then it smoothens out. And so we neglect the transient phase and go for the smoothing out function, or we...
So f of x is a function of x, right? So to talk about the transient phase, you need to interpret x as time, and then it's not a design parameter. Now, if you mean that it does, the more you know about f of x, you can encode that into your Gaussian process. Okay, you can encode it in the Gaussian process. The more you know, the better this algorithm is going to work. But the point I want to make is the following thing. In a real application, you have no idea what your f of x is. Let's say you have a website and the f of x is the number of clicks you get if you use these colors. What is f of x? You don't know what it is. Is it smooth? Who knows? Does it have discontinuities? You don't know. And you can and you want to optimize it. Okay? You want to optimize it because you'll make money if you optimize it. So you say, okay, I can just randomly try out x's. You could do that. You will find something. Or you could say, I'll do Bayesian global optimization. What I'm saying is that Bayesian global optimization will find something better than the random things. Will it find you the global maximum? No, it will not find you the global maximum because this is not mathematical theorem, it is an actual practical example, right? You cannot convince anybody that that's the global maximum. Is it going to do better than random selection? Yes. Are there cases in which random selection will do better than this? Yes, there are. When your function is like this, okay, then random selection would be better. Randomly trying out stuff. Okay, so we are kind of done. Just want to leave this here that you can actually, we just look at maximizing a deterministic function without constraints, but it is possible to add constraints. There is literature on that. It is possible to do multi-objective optimization, so have two objectives and gradually pick designs that will give you the Pareto front. It is possible to do optimization under uncertainty, maximize the expectation of f of x while you're averaging over noisy things. We have papers on that that you can look up. What else? And you can also do this kind of information acquisition when you have from different information sources. You may have an experiment, a simulator with a low fidelity, a simulator with a high fidelity, and you can say, I want to find a design that maximizes this objective, and I can pick at any time to either do an experiment, prototype something, or do a simulation. And you can pick between these.